My talk is about profiling tools for Java. I want to answer the essential questions: which tools are they? Why should I profile? Which tools are they? How can I use them? How can I obtain them? And how do they work? So the normal W questions. So who am I first? I'm Johannes Bechberger. I work in the submachine team with several other colleagues doing work on the OpenJDK. We, for example, do the updates for the OpenJDK 17 project. And I started there working in January this year, and since then I worked on different projects. For example, I started work on I started then to work on Async profile, which is a profile that I also present, making it safer, helping with some bugs in the PowerPC port, and also working in this area, making the APIs that Async profile uses of the OpenJDK safer and more stable. And for this reason, I also started to write a Java enhancement proposal. It's called Asynchronous Stack Trace VM API, which helps profiles to gather asynchronous stack traces from your JVM, which is quite nice and which in the future will help profiler writers and also has other advantages. But I come back to these two later, and also to a project that I started a few months back, which is that I wanted to use Firefox Profile, the profile integrated into Firefox, to show JFR data, like Java profiling data, properly, and also create an IntelliJ plugin to ease the burden of installing a profile and doing all the stuff till you get to your simple profile. So now to the introduction. I essentially will answer here the question why. I have here a simple example program that just counts events. So it's an example program that came kind of up in the work that I did for making profiling data usable in Firefox Profile. And so this application has two parameters. For one, it's a file that you pass in that contains a list of events, and then you have uh, a regular expression that matches for a type. So the idea is count all events that match this type in this field. So first we get in an event store, and then we ask the event store, give me all the types that match this regular expression, and then we just loop over the list of types, get the events for every type, get the size of this returned list, accumulate it, and ta-da! It's a simple application, but it shows us some interesting details, and I will use it in the following for all the examples. Um, I hope anyone can understand it. I originally tried to use a more complex sample from the Spring Boot world, like the Spring Boot path links, but I think this will illustrate it better. So now, we found after some testing that it's slow. So it took almost a minute of CPU time to execute for a rather simple regular expression. So the regular expression is not a problem. It's just a two-part regular expression. So and then we used a large file like 160 megabytes of data and executed it on my Mac, and it took 1 minute of CPU time to execute. Any guesses why it might be slow? Any guesses? Hmm. Yes? Oh, sorry.
So it goes through the whole file every time you do get events.
That's an interesting point. Yes. Other ideas? Okay. The thing is, these are nice suggestions and they're quite obvious, but the problem is essentially what we're doing, and when we're optimizing the program based off this, we're doing essentially pre-match optimization. And there's Donald that you probably all know from his signature book series. Um, But he also wrote a few years back, we should forget about small efficiencies, say about 97% of the time. Premature optimization is the root of all evil. This is the short part that's quoted everywhere. But the interesting part comes afterwards. What he also wrote then was, yet we should not pass up our opportunities in the critical 3%. A good programmer will not be lulled in complacency by such reasoning. He will be wise to look carefully at the critical code, but only after that code has been identified. The important part is this: only after that code has been identified. Yes, we can look at the code and say, oh, we identified it, but let's ask a profiler and let's really identify it. We zoom a bit in this profile. This is called a flame graph. It's like the basic visualization created by Brandon Eck, of which of whom I show a video in the end, which made him famous, kind of. But yeah, we have here flame graph, where it essentially tells us when we zoom a bit in a part, is that the main method here, the main method here calls the count events, call again the event, calls read events, as we see here. The main method has to call this count events for it to be an application, and then count events calls get events and also calls the get matching event types. And the width of the bar just says how many samples, how much time the method took of the method that it called. So for example, in count events, we see that clearly um, around 82%. We don't see clearly that it's 82%, but essentially we can look at the data and ask the tooltip, hey, how much is it? And so we get that it's around 82% of the time that of count events was spent in get events, and around 70% was used in get matching event times, and the rest was used in these methods like size and store, but we don't see them here because they aren't really important here. So this is essentially what the flame graph tells us, and also it tells us when no method is on top of a method. For example, here it tells us that the method also took on its own some time to execute. So this is a basic concept because flame graphs really allow you to see the whole picture. And so one could imagine that we saw it then that 82% of the time was spent in the get events method. Yes, we could we could exchange the loop and put in somewhere else and merge it essentially in get events, but we're not doing it here because it might be an application. We have other applications and say we cannot change the API of this event store because it's some legacy code which we might improve, but usually we have the case that an API change would like require a enhancement proposal or something in larger, especially larger open source projects. And so we would say, okay, let's try to improve it. But what is this code? It just reads all events. This returns a list of events. Then it uses Java Stream API to filter it. It matches the type, and then it then it returns a list. And so what we see here that most of the time, almost all of the time, is used up in this read all events method, and then a bit on the toolList method, but toolList is really a cheap method. And also, almost none of the effort is spent here in this method, in the matches type. So regular expression isn't really a problem. Does anyone have an idea how to improve this method?
Call read all events once and then do the filtering for each type.
That's an interesting idea. Any other ideas? Okay. So I expected this, but we have to then we have to look at the whole flame graph. Because I skipped over it purposely. Maybe some of you saw it in the beginning. I skipped over it because when you look at the whole flame graph, this flame graph also gives us the native call six, like the C++ code that was executed. Not only the Java part there, which is really, really small. So we'll look at the real part here, because when you optimize this like by factor of 3, it will get probably better the runtime, as essentially this, the used CPU time. Well, look here, the experienced OpenJDK developer knows that G1 is a garbage collector. So essentially what this code does, it garbage collects a lot. And then we think again and see that maybe we're allocating a lot. Maybe this isn't that good. And so what we do is we know that this underlying API that is like read by read all events has some kind of iterator functionality. So we get an event, we process it, we store it in a list, we get the next event, and so on. That's essentially what this code does. The API is a bit more difficult, but it's essentially does. It says, while you have more events, read the next event, matches the type, edit, and on. And now the interesting part is that this reduced the amount of garbage collection that we did and the amount of time we spent in this garbage collection code essentially by factor of 3, which is quite nice. So in the end, it took only 20 CPU seconds versus the 60 CPU seconds. With a simple change, without any of this caching that one might use. For example, we cache this file and so on. And it also reduced the overall memory load of this application, which is also important, especially in cloud applications. So what we saw here, that you don't, that trust your profiler. Look at the profile. Don't use just your intuition, but try to add facts to your intuition and use it. And if you're wondering how to build these flame graphs, I come back to it just in a few seconds. And there's also some demo repository where you can grab yourself the tools and try and create a flame graph like this. But now to the part where I ask you questions, and hopefully, please, not only one person answers. Who of you used the profiler before for profiling Java? More than I expected. Yeah, some people just waving. Maybe they didn't know what a profiler was then. I'm getting to the different profilers later. But which of the profiler has any one of you used Visual VM? Oh, it's more than I expected from the studies that I read from Jay Rebel. Any other profile that you've used? Anyone? Might anyone give them the thing back and just throw? um, what did you use? Of course. Something else? Another profiler? Oh, we're getting the whole picture. That's nice. It's better than expected. Anyone else? I know that some of my teams use their own sub JVM profiler, but I think that doesn't count here. Yes? Uh, what? Yes, sir. These are really nice people. They are from Germany, I think. I could well recommend working with them. Okay, now we're the whole list. Oh, that's more like the industry. Like, what are their own profiles? Essentially, the only one missing was like the sub JVM profiler and the Oracle Studio profiler. So interesting. So I of course expected that many of you said Visual VM because that's like the question that I myself answered before starting on this whole journey working at SAP. And I tell you later why you don't want to use Visual VM in certain contexts. It's a simple tool, it's cool, but don't trust Visual VM that much. And if you don't trust me, there's a person who has a scary image on his slides to tell you this like half an hour long. So now the basic question was profiling, and I chose a definition from the Jargon file in which someone wrote, it's a report on the amount of time spent in each routine of a program used to find and tune a way hotspot in it. That's essentially what we did before. We used it to find a hotspot, we saw its GC, and then we thought, maybe reduce allocation, fine. or used it otherwise. There are different kinds of profiling. So people might understand under the term profiling, method profiling, allocation profiling. These two we kind of cover here, especially method profiling. Then there's something like log profiling, GC profiling, DB query profiling, and so on. But that's maybe for future talk, or maybe one of you could talk probably better on it. But I'm going to cover especially the top both. Now to the part that's really important for you probably. So when you get out of this talk, you probably want to just remember the slides that come. So it's the really important part of this talk. When you use Async Profile, some of you have used this before. Yay, it's a cool tool. You just pass Java some options that you pass for every profiler, because Java needs some you need to tell Java that you want to get more precise profiling information. It doesn't really affect your performance or your memory footprint, but it's still not on by default for some reasons. Then you tell it, please, hey, use this agent. You can download this SO file. It's on Unix. It's an SO. On Windows, it doesn't exist because Async Profile doesn't have any Windows support in the open source world. JetBrains has one, but it's sadly closed source. So then you have your library, and then you tell it, hey, please start, and you tell it which CPU events to listen to. Usually you want to use CPU or wall clock, and then you tell it which file to which file to store your flamegraph in, and then it help make a flamegraph. But it can also do other things like produce a common format that the next tool exports, and you can also, of course, attach to a running Java process. And then you get, when you execute this graph that you've seen before, because I essentially used Async Profiler for all the flamegraphs before. Then there's JFR that some of you also used. It's like the Java flight recorder. It's kind of the standard format for profiling information for Java, and it's built in since JDK 8 into Java itself. So you have these both options as before, and then you tell it just start a flight recording. You can add some settings to get more or less data, and then you tell it where to store it in, and that's fine. And then you get a JFR file that you can view with different tools, and you can also use JCommand to start and dump the data then later. And what's really cool is that someone recently developed a Spring Boot educator endpoint, which you can use to have an endpoint in your Spring Boot application where you can say, please start profile, please enter profile, and give me a flame graph. And the really cool part, yeah, it's included there in your OpenJDK. You can just use it and be happy, and it works on all platforms as far as I know. And there's the common way to view it. It's the JDK mission control. You can get it from different vendors like Adoptium, it's kind of Eclipse, Azul, Biosoft, Oracle, and of course our team. But it's coming soon to our Submachine.io website. And you can use it to view data, as I said, from different sources, because JFR is such a common format. Async Profile supports it, and also other tools. But I tell you later why I would recommend to use Async Profile in combination for with JDK Mission Control. So how does it look like? If some of you haven't seen it, it's essentially it has a splash screen where it tells you like, hey, what's kind of going on in your application, and it tells you clearly here that the garbage collection is red. It tells us that, hey, you did a lot of time in garbage collection, and it also tells you your Mac hasn't enough memory for this class. So it tells us here essentially that during this benchmarks, my Mac was running out of memory and was using like 15 gigabytes of swap, which isn't probably the best case for an evaluation, but I had to work on the slides during other things, yeah, like using Teams. So that's it, and it made for a good evaluation. Then when you look further on it, you can get method profiling information where you can get your flame graphs and your other information. It's essentially a more extended version of a flame graph that you can see. Then there's another tool that I started to develop this summer, which is a pretty early prototype. I'll show it later to you, but it still contains error, but it's essentially the idea to have a plugin into IntelliJ and later other in IDEs to just be able to profile code in your IDE. For example, here we have this invent filter app that you've seen before, because this is like the count events type method that I've talked before. And then there's the main method, and you then can just right click on the method, and then besides the run, debug, and run with coverage, you have now profile event filter app main. And when you click on it, it runs a bit, calls JFR on the whole thing, and then you have a nice view of this file, and it also allows you to view arbitrary JFR files, and you get your flame graph. You can select the time slice in which you want to see more information. You can have the heap memory, you can have the CPU load, and also the load of the main method here. And there's some other options, but I think I tell you later about it. And you can get it under my GitHub link, but I don't have put it anywhere else because it's really still not a prototype. Any questions till now? Okay, no questions. Then we got to the obvious thing. There's no free lunch. What is the performance impact of this all? So one is that many people are asking like, yeah, I can use JFR, I can use Async Profile, but doesn't make it my application like 200 times slower. So why should I profile it then? Um, so I just run a benchmark. It's like a benchmark based on the Capo. It's a common benchmark suite, and it took around 48 seconds on 8-core machine, and it has a quite high standard deviation. So it's there's a bit of noise in the measurement. So I tried JFR with a reduced setting that's like for running at longer times, and you have an overhead in my example between 0 to 5%, but it's typically around or lower than 2% in the literature. Then the file that is produced, the JFR file, is between 650 kilobytes and 5 megabytes, depending on your specific settings. Then there's JFR in the profiling setting. You get a bit higher overhead, but it's usually still lower than 5%, with around 6 megabytes JFR file size. And the same is essentially true for Async Profile and also for Async Profile with JFR Sync. What JFR Sync does, it tells Async Profile, hey, use all the things that you can do, got method profiling, and it tell you later why. But use also the JFR data. So start JFR, combine the data, return it, so you get all the good parts of Async Profile with all the good parts of JFR together. But this increases, of course, the file size because Async Profile on its own produces a larger file because it contains more information typically, and increases also the overhead. But usually the overhead is like lower than 5%. But profile your application or time your application with the profile on to see really whether that's a problem, and then you can adjust the settings on how accurate and how less approximate your results are. Any questions to this? Like, yeah. Yes. No, no. So so it's essentially around this. What a profile usually does, it works continuously. It stores continuous data. So no, you don't have any one time where like your profile is using 100% of your CPU and your system is like screwed for 1 minute, and then an hour long you don't have anything. Um, But it will depends on the application. It depends the overhead on the amount of threads you have, on the deepness of your threads, and the amount of data you're collecting. But you can adjust it. So there are many people that using Async Profiler in production that just runs beside their code. So when they have like a problem in their code, they can just go back to the JFR data and say, "Oh, I have this." There are also companies that are integrating this information into the tooling. There's, for example, Elasticsearch that have the application property monitor agent, like the APM, um, just running all the time, because it's worth for them to have like 2% performance penalty for knowing what went wrong. Any other questions? Okay. Have any one of you used actually some of these profilers in production? Like run it or yeah? Maybe what? Oh, yeah, cool. Someone just said JFR flight trigger. Yes, that's a common thing. JFR is like marketed as being able to be run just aside, and that's also what many people are doing because it's cool. You get all this data, and they show you later what amount of data you're getting. And now for something completely different. You came here for the interesting part, like how do I use Profiler, and you're probably satisfied, but I'm not kind of satisfied for only giving you this because that's nice, but I'm working at a team that helps developing the OpenJDK, so I'm interested in the deeper layers. And now you had this more toppy layer, and now we're getting with each section, there are two, and then the demo, we're getting deeper. And now the first step deeper is like, I'm giving you the basic concepts of profiling and writing profiles. So if you ever wanted to write a profile, which might happen, it's quite nice to work on it, and you get many more insights that you want into segmentation files and everything of the OpenJDK. I speak from experience. But now there are different types of profiles, and these types aren't really clear cut because many of the profiles that essentially do one thing can also be told to do the other thing. For example, async profile contains both of these types, but usually only uses one. And so the first type is instrumenting profilers. Essentially, what you're telling the profiler, just insert some instruction in it. It usually uses a Java agent, which can automatically modify bytecode. So essentially, when we have our count events method, it adds in the beginning a log entry and says, "Hi, I'm starting with this method count events," and then on the exit it tells some library behind, "I'm ending with the count event." This is pretty cool because it's quite accurate. You get every call of this method, every exit. It's essentially like when you're doing a printf at the beginning and the end, and at the end you have a printf that tells, "Oh, this method took n seconds to execute." That's essentially it. So it's accurate. The problem is it's slow. You're counting every call, especially when you're doing this for all the methods. It's quite hard because you're calling a lot of methods. The other problem is it's kind of distorting because it's so slow. It's distorting, but also this is code that will get to the JIT that will do some memory allocation. So this is a bit problematic because it distorts your results, and you might not be getting the same results because optimizations are differing. So essentially, you're profiling a kind of different program. Um, but there's like the thing that all the modern profiles essentially do, it's sampling profiles. So when we have this example here, we essentially ask the JVM in regular intervals, "Hey, what code are you currently executing? What's your stack trace?" Essentially, it's like we throw an exception, we create an exception and get the stack trace, store it away, and do this like every 10 milliseconds. And then we see that in this method, in around 2 times here with an interval that's like matching, we find that the method is executing get matching event types, and then a lot more times, around here 8 times, we see that the stack trace includes get events. And this has the advantage that it's fast. We're only asking the JVM like 10% of 10 every 10 milliseconds this information, and not always when it's executing the method. Because in usual programs, when you have a loop and you're executing lots of methods, then you would be asking like every nanosecond or every microsecond this question, which really it slows everything down, and you get overhead figures of like well above 100%. But it's only approximate. You only find methods here that are executed when you're asking every 10 milliseconds. You only get methods that are executed longer than 10 milliseconds or around 10 milliseconds on average. So we don't see the whole picture, but usually for profiling we only care about the methods that are executed often. And now there's the topic. But now, does anyone have questions with like this distinction between sampling profiles and um, instrumenting profiles? Yay! Um, yes. The problem with long call stacks is that uh, when the call stack gets too deep or when the stack trace gets too deep, a common thing is that the profile just cuts it up. So what you see usually with sampling profiles that you have stack traces that begin somewhere in the middle because the stack trace it starts at the top and then runs usually around for JFR I think it's 64 frames uh, down or down or up. It's difficult for stacks because it depends on where you're a computer scientist with a PhD or without a PhD in which direction you look at. But essentially, you only take the first like 64 frames on this call stack, and then you just discuss the rest because you think that maybe these really deep call stacks aren't that stack traces aren't that often because in commonly in Java you don't have that much recursion in it. But yes, it might be a problem, and when your overhead is too high, it might be that your stacks are too deep, and then you just decrease this depth. So is this clear? Okay, you can ask. Yes. Yeah. That's Yes, that's so. This is one of the main problems with instrument profiling that it's really distorting. So you can prevent this by just logging some specific methods. You usually do it like you do it with printf profiling, should I call this? Um, so you do it just for specific methods that you really are interested in, like your 5 methods, and then this isn't a problem. But yeah, it might be a problem, and that's a cool thing about sampling profiles. It isn't it isn't the problem for sampling profiles here because for one we're just taking like every 10 milliseconds of stack trace, and also this doesn't really we stop this whole JVM turn. We yeah, partly I come back in a few seconds which parts we're really stopping, but essentially we're stopping things, and so we don't counting the time that we executing it, which is quite nice. And also the time is a bit lower because instrumenting profiles uses Java, and the normal sampling profiles are written in like C, C++. And the first of these was um, kind of developed by the Oracle, and but then at this time some people that have their Oracle Studio where they use the same technique that they use to profile C++ and C applications to also profile Java applications. So it was written in C, C++, it was fast, and they got far better examples than when you use instrumenting profiles. Instrumenting profiling is something that Visual VM is like the only one that I currently know that really relies heavily on it when you tell it to. All the others just have it as like a thing that you can do if you really want to know if you really want to know what this method does. For example, here it could be cool when you want to really know how much time this get events method takes and the get matching event types. You just wrap it there because then you get really precise information. So, any more questions? Okay. Cool. Um, so now I'm telling you about a point that's called the save point. So essentially, when you have your small thread that runs around, you see it's transparent, so the state isn't well defined because it's in like a loop that's JIT optimized or something like that. And there are short pulses where it's non-transparent. So this is time where it checks a variable and says, hey, I'm at a kind of defined point, should I stop my thread? It's essentially like when you're doing a thread, when you're implementing like a thread with a loop that loops along and you want to stop it, you usually have this pattern of setting a boolean variable in it, like an atomic variable, for example, that you can switch on and say, hey, please abort this thread or please hold it currently. So that's a save point. One of the main purposes in the JVM is that when you have garbage collections, you want to have the thread in a specific and in a defined state, for example, garbage collection, JITting, and so on. And you can also use this for getting call trace. So you can get call traces just at such a save point. So what it looks like is like with using save points, you have here your thread, and you ask it, please stop, please. But when you're ready, when you're in a good state, and now you stop it, and it stops only when it's like in this non-transparent state, when it comes up to the surface and says, oh, give me some commands, and you tell it, hey, please give me a stack trace. Which is cool because the state is defined, but which is also problematic because you're waiting a long time between like, please stop, please, when you're ready, and it will stop. So it's a bit of distorting. And then you have the asynchronous way, and here comes the JVM. And then you say stop, and it stops immediately. So it's probably in a state that isn't at a safe point. So it's kind of undefined, but it's cool because it's not distorted. And then it's even more interesting with multi-threads. So we have again the submarines coming in, and you say, please stop when you're ready. The first is at, and then you wait till the second is at a point to get your stack trace. So it's even more distorted, and you even have a larger performance impact. Because the thread 1 essentially waits and will till the second thread is at this point. And with asynchronous, you're saying, stop thread 1 because you only care about one thread, because you don't need to have the whole JVM at a defined state. And you just stop thread 1, work on it, and then you get to thread 2, say, okay, please stop. So that's really cool. And the main difference between like the Visual VM like profilers and most of the other profilers is that Visual VM is like this profile. That is, please stop, please, when you're ready. And all the other profiles is like, stop. So therefore, I would really recommend using JFR and Async Profiler, or Async Profiler, because both just give you an accurate picture, and they should have typically a lower overhead because of this here. But of course, they have problems. They have the problem that when you look at the top of your stack here, that it might be a bit squishy. So you might not know which the state currently is. So you might be in the middle of copying something in a JVM. You might be in the middle of a JVM internal function that does something in the middle of like JIT, in the middle of maybe a garbage collection. So it's far harder to know where you are here. So the people that wrote this API that does the stack walking really had to look into how to do this without segfaulting your JVM, which is like one of the worst cases that you can do as a profile. Like, oh, sorry, I segfault your JVM. I had cases where I tried to test crashing a JVM, and I had cases where I was able to crash a JVM like every few seconds, which was quite cool with some certain settings. But it's now better. I worked on it, and also the profiles got a bit better. But what are differences between JFR and Async Profile? Because both use the sampling technique. The difference is that Async Profile captures also native threads. As we've seen before, it captures like the C++ frames and also their threads, because it does native stack walking. And it has far less discarded threads compared to JFR, because when Async Profile sees this like cloudy situation where it doesn't know anything, or where it might have problems finding the stack trace in the first try, it wiggles around like the starting condition with which it calls the method that gets it, this call trace. And so it says, oh, maybe when I adjust the stack pointer one up, one down, maybe when I adjust like the program counter a bit, the frame counter a bit, and just a bit of wiggling, it costs a bit more time, but it reduces the number of discarded threads by a lot. And so this is also a reason why many people are just using Async Profiler as an API for this whole async stack trace getting, because Async Profiler is actually that good. And yeah, I tried working on making the methods here a bit better. They do all this collecting, and I worked with my colleagues on reducing the amount it segfolds, and we're getting it down to a good amount. Essentially, um, I would now recommend to collect the data with Async Profiler, like with the JFR sync, as I told you before, to collect all to use JFR where it's good for all the cool events that it also adds, and Async Profile for like the native stacks for the method profiling. Um, and yeah, there's slight debate whether it's safe. I think there are the people like me that tell you, okay, yeah, this is safe to work this thread this way and just wiggling around, because tests and experience. But there are other people that have valid remarks and say, okay, maybe when we just have the probability to crash the application or to maybe corrupt the data, we shouldn't use this. But this is an ongoing debate. If you want to get a glimpse into this debate, I've linked the pull request where I discussed it a bit here below. Any questions? Any questions regarding this here? Okay, good. So what does JFR events add? I said before that JFR brings lots of interesting events, and it has events for, of course, method and recursion samples. But you would really like to use Async Profile instead on the supported platform. So when you're on Windows, JFR is your only bet. Then it has information on garbage collection. For example, you see how long the garbage collection took every time, and you have information on I/O. But our team is currently working on to improve it, and there are also other people that trying to add new events to make it even more comprehensive. And then you get system information like your CPU, your memory usage, and everything else. And you can even add your own events, and they then appear in the JFR file and can be processed by tools that use JFR. But overall, profiles are lying hobbits, as Nitzan Vakar told in the talk that they've linked here, because yes, they are kind of approximate, but also things like the correct things like the line number. It isn't really that correct, because you have CPUs that are like SuperSCAL that execute multiple um, um, instructions at one point in time, and you have also compilation in it, so and inlining and everything. So profiles are giving you an approximate image, even if you're certainly that it's kind of right what they're doing. Keep in mind that they are lying hobbitses. um, but it's usually okay to just use it as a tool for investigation and then draw your own conclusions. Don't rely on them being really the ground truth. So then after this more after this discussions of the types and the basics, a bit of a history of profiles, because many of you have probably used different profiles, at least some of you, but there are multiple there, and there are three categories. And the first is like the chain axis or get call trace based. This is the thing that I told before. It has the a safe point bias, and you have tools like JConsole or Visual VM, and I think it's similar code is also embedded into NetBeans profile. And these are methods that are quite old and quite easy to use, because they are also simple for profile writer to use. Then there's async get call trace based profilers. This is like the asynchronous way to get stack traces besides JFR. It was first introduced, as I already explained, by Oracle Studio or Sun Studio at the time in the Photo Analyzer tool, and later the API that it used was used by Async Profiler, and before it some other tools, but eventually then Async Profiler to make it usable in an open source way. And there's at the end the JFR-based tools. So JFR stands for Java Flight Recorder, or nowadays JDK Flight Recorder because Java is a trademark. First, it was created for the JRocket runtime analyzer. It was like an internal tool of a small Java VM company, and then it was bought out by some different companies. And then a few years later, it came to Sun and Oracle, and they renamed it to first Oracle JRocket runtime, Oracle JRocket Mission Control, and then later to Oracle Mission Control and Java Mission Control, so it's a bit of confusing the name, and so it went to be the Java Mission Control, but the problem was at the time it was quite expensive. So someone in 2013 wrote, Fabian Lange, even with a seemingly superior technology, because JFR was at the time really, really nice, the production license of Flight Recorder comes at 5,000 or 15,000 US dollars. So bit expensive, and that's kind of the reason why many people didn't use it, in my experience, and why I as a student didn't use it, because I didn't have enough money to like shell out $5,000 for just profile my Java application. I took the Visual VM because Visual VM was like in the JDK from Java 6 to Java 8, just Berlin, and it was fine. And then Oracle open sourced it, so there's a headline from the time, it was in 2018, and that tells you Oracle lays off Java Mission Control team after open sourcing product. It's not kind of death by open sourcing, but because then afterwards people started to work on it. Essentially, people that worked before on this project worked on it in different companies. For example, Datadog does some work on it. So it's a thriving open source project. But yeah, it has a long history. It has history from like I think 2008 or so. Um, and so yeah, so from these profilers commonly used are currently like the Visual AM NetBeans, Async profile and JK Mission Control. There are also other proprietary profiles like JProfile or Yocod that essentially lie at like somewhere between here all around, because they use async get call trace. I talked with people from both companies. They use async get call trace and for the internal profiling, but I think they also rely on other methods like JFR based, and also get the information from like the Java management beans. And there's of course internal profilers that, from for example the sub JVM profiler that SAP developed, that use their whole internal um, code, because it was based on SAP's own JVM kind of. So, any questions for this part of the talk? Yes, without waiting till it is at the safe point, so it's accurate. Cronus method. Mm. Yeah, so commonly what async profile was based on, so not code wise based on, but the idea was based on perf. You probably, some of you know probably the perf utility from the Linux world, where you can just ask a process, where you can just walk the native stack of a process. And one of the first incarnations of the async profile like idea was that they had a perf map agent that essentially gave perf the ability to walk Java stacks, um, and gave you the information. So yes, you can just, I think for Node.js and also for other runtimes, you could just probably use perf and it works fine. The idea of the perf match agent for Java didn't went that well, so they had problems, and it's essentially now a product that doesn't work for modern JVMs. So async profile is like the reincarnation of perf based, and it also uses some of the functionality of these perf based tools. Oh, yeah. So when the question is around skirts, yeah, yeah. So I think I can answer this a bit. So then also the people on when they watch the video notice. So it currently there's the problem with async frameworks like with Project Loom, and currently what the profilers do. The profiles I know of just show the threads on the carrier threads, show the frame on the carrier threads. So there's not that much specific handling currently in JMC, JFR, and Async Profiler for these Loom threads, but I think there will be ideas how to deal with it and also how to visualize the lots of threads. But currently, you only see it on the carrier threads and only if they're running. Yes, that's not the best option, but it's still undecided what to do else and how to do it in a performant way, because when you have like 1 million threads, you can't really visualize them like one besides each other because it won't make sense. So yeah, it's still hard. Um, and I try to look into how to work with reactive systems, so you can use JFR events to say, oh, I'm in this reactive thread and I'm executing something, but it's still very hard to do, and it needs far more cooperation from the writers of the reactive code. Okay, yeah. For those in Java 8, um, upgrade is a good way. Yeah, please upgrade. I can tell you from the experience of a team that um, uh, that works in this field. Please upgrade it. Java 8 isn't that great. Use Java 11. You get new Java features and cool new OpenJDK stuff. So when you're in Java 8, Async Profile I think supports starting at 6 or 7, JDK 6 or 7, so you can still use Async Profile. I think JFR was ported back to Java 8 too, so essentially all the things that you see here you can use with your Java 8. Um, I think for the analyzer also works with it. It's old. It kind of works on Linux only on the Oracle Linux. I didn't try it, but maybe you can try. Um, and Visual VM also works on, should also work on it. Yeah, so I have to tell you from so from someone Guts, for those who don't know, is like the updates maintainer for I think JDK 17. 17. So what he said was like, yeah, Java 8 is okay, but we only backport the new cool stuff and also most of the bug fixes to like JDK 11. So please consider switching. It makes the life of OpenJDK of JDK writers far easier. So yeah, but now I advance a bit. So I told you that I got down the slippery slope of getting more detailed and more detailed and more detailed, and so now we're at the most detailed part of this talk. Please stay with me. There comes the demo afterwards, and then pizza. So it's about async get stack trace. It's the chap that in the beginning that I mentioned in the beginning. It's for the OpenJD contributors and profile writers in the audience. Essentially, hi guts. It's essentially for my colleagues, but I think it might be also interesting for the people here in the audience that want to know what this async get stall trace is, because in many talks on this topic on profiling, you hear about async get call trace and not that many people explain you the hard details. So, async get call trace is like the unofficial API that's used by everyone. It was implemented or added to the JDK by Oracle and or then Paul Isan in 2002 in November, and then removed from the official pages in like February the next year. But since then, it's still there. It's official. People use it. For example, Async Profiler uses DLSym methods to really to not link to it, but to get the symbol and then call directly, like from a memory address. But it works. So what it does, you call it in a signal handler. So how the sampling profiling essentially works is that you register for every thread a signal handler and say, okay, if I send you a signal like sick user, like you use a signal, please get into this handler, and then you parse this async get caller as a pre-allocated trace, because in Ziglander you cannot allocate something on the heap. And then you pass it how many frames you can store it, because this is C. You don't have any size information, you directly add frames, and then you parse it. The U context is the context of the thread that you currently interrupted. Your signal handler gets it. And what async get call is then does, it walks your stack and essentially returns the information on the Java frames and also on the frames that are like the border between Java code and native code. It's in the profiler speak, it's called a native frame, because it's like the methods that you declare with the native keyword that you have in Java, and then you implement them in C++, and you get the line number, which is like a misnomer because it's the bytecode index, but then you also get a JMethod ID, which is like a pointer into a VM data structure that gives you a method, and this is what it returns. It has some disadvantages currently, so it misses important information like inlining, compilation, and everything, and it also misses native frames, because when you consider a stack, you walk it from the top, and then a tool like Async Profiler can walk native stacks. So you have native stacks on top. For example, when you read a file, it has like this system IO on top, and then it works, and then you come at a point where you have Java code, and then your async call trace kicks in, and you call it and say, oh, here. Um, uh, and then when you have in the middle Java native code, then below, then async get call trace cannot have it, because it doesn't give you any information on native frames. But also async profile doesn't know it, because it doesn't know where the frame pointer and the stack pointer for these frames where to start. So that's not that great, and also it's an unofficial API. It might disappear sometime. It's not declared anywhere. Um, so what I then tried in January and then February, I thought maybe I could add another API, because I thought, hey, I only started like 2 months ago at this company, and maybe I just add the Java enhancement proposal, because that's what you're doing when you try to do a PhD before and then get through. You try to get a Java enhancement proposal, and it looks kind of good. So I got last week the I got 2 weeks prior. I got the information by Mark Reinhardt that it's now an official draft Java enhancement proposal. So you can view it on the homepage of the JDK, and it's an extended and supported version of async get call trace. So for one, it should be support. You should have a header that you can link to, which is cool, because you don't have to do some DLSym magic. And it has an API that is quite similar to async get call trace, with the only exception that you put it some option here, so we can extend it later, because this is what async get call trace misses. We cannot add information like, please add this information, include these frames or not. Currently, there's only one option, like include me these C frames that async get call trace before just skipped, please include me these. So it gives you some information. For example, for a typical Java frame, you see here that I get encoded in the type, I get whether it's inlined or it's Java, and also whether it's a native method, because a native method is kind of, it lives both in the native and in the Java world. You get a compilation level, you get a bytecode index, and you get a method ID. And for non-Java frames, you just get um, the program counter. So it offers a lot of advantages compared to the current API, and it also makes is and it also is easy to implement for Async Profiler and other profiles to work with. And I had discussions with profile writers, for example, with I mailed with the people from YorkIt, from JProfile. I had exchanges with the creator of Async Profile, Andre Pangin, and I also talk with Datadog people. So it's really a thing that they approve and they will like it. So I hope it gets um, to be a Java enhancement proposal. And the other cool thing is that in this proposal, I will also add in the implementation in use Stackwalker. Because the problem currently is that essentially every code in JVM at many places copies the stack working logic. So essentially the stack working logic of async get call trace is kind of the same as in JFR. So what I create what I started to create was a stack worker API that can be used for both. It's a simple API that you just say okay some basic information, and then it's just an iterator. You iterate over all the stacks, and then you can say here in the beginning like, hey, should we skip C frames? If not, it gives you C frames. You can ask it, hey, am I at error? And then get some error code out of it. Then you can ask it, hey, is it a Java frame currently, a native frame, is it inlined? And just work your way down. It's pretty simple to see. That's essentially the whole implementation of async get stack trace, which I will like. And so I hope it really gets in. So any questions to this technical part that I wanted to sneak in because I thought maybe someone is interested? Any questions? Okay, I hope I didn't lose you there. So now after this, I have the demo. Um, but before I give you a demo, I wanted to give you the resources. Some resources are like I created a playlist for YouTube where you find all in some interesting talks, and I hope you also find this talk when it's interesting for you. Then I have a GitHub repository for this talk where you see in a README the users on Twitter that you can follow, blogs that might be interesting to read, and also some sample code and also some tutorials I found. I'm glad if you like this thing that I put there on, and you can add new information using pull request or issues. So I'm happy to increase it because I didn't find any such collection that is like not specific to one profiler anywhere in the internet, and I didn't find playlists of Java profiling talks from all over the conferences. So yeah. So now to the demo. I hope it works. Um, Good. It's mirrored. So first, my IntelliJ plugin. I show it to you as an IntelliJ plugin, but it can also be used just standalone. You can just convert your JFR data into the Firefox profile format and use the typical Firefox profiler that you find under profile.firefox.com. So how to use it there? Um, Oh, of course, yes. Sorry, I it's, forgot to make it bigger. Uh, Thanks. Increase font size. Oh, glad there are people here that think. Oh, does it? Ooh. So yeah. So this is the whole eventful tab. So yeah, that's all. And you have an event store. So it's my SAML application. So here, um, you usually just click on it and profile, but you can also right click it. And then you have this profile icon there, and we can call it. And then I have 1 second, hopefully one minute to talk about something different because it takes a long. You saw it before. It's the original version that takes like some CPU seconds to run. So it's an IntelliJ plugin that's currently a prototype. It might disappear in a minute. You can try it out, and I'm happy if you do. Currently, I think I don't have any build versions on it in my GitHub CI, but maybe soon. And it's just like a proof of concept, and then you search it, execute the JFR there, and then it launched the JFR file. It just creates by default a profile.jfr file. You see it here, and I hope I can zoom in. Okay. Okay. Sorry if I don't. Okay. Sorry for not being able to zoom in. Is this kind of legible? Uh, yeah, sorry, I didn't think about this. What you essentially see here, if you see anything, is that you here have the memory part, where you see the memory that the program took. You see here the CPU load. You see what the main thread did. You see this like curve where you see, okay, these are times where the main thread executes something or didn't execute. You have here your call tree. You have your function table of like the hard methods on it. You have a flame graph, which is essentially the same as with async get call trace and the other things that I've shown you before, with the only difference that I chose here blue for the methods in your application and gray for everything else. And then you can have tooltips where you show where you get specific information like how many times was this inlined or how many times was this use compiled. Um, and then we can also do this for other things like object allocation samples. Where did all the object allocations appear, and what maybe people in the first row see that we see here that patterns are often allocated, and that one of the things that I could do in my app to improve it is they just recompile the patterns, because lots of patterns are here compiled all the time. It's like, I don't know, 1/8, 1/6 of all the compilations of all the allocation is just here, but you also see here that the whole parse.me file did produce a lot of allocations. Then you can see here the marker chart, which is essentially gives you all the markers, like all the events in JFR speak that came here, and you can use this for your advantage because we can select here part because we think, oh, why is the memory usage dropped here? We can look into it, and you see here some long bars. This is essentially the time the garbage collection took. So we saw, okay, the memory dropped in this area, and this is the whole, and during the whole time the garbage collection went, we can get more specific information. Currently, it's not like improvement and not collected multiple events together and made it easier to read, but that's something that maybe comes in the future. You can also get the specific information. So yeah, that's what I did like for 2 months, and hope you like it. And it's also open source, so it's currently on GitHub with an open license. Yeah. Any questions for this? Do. Thanks. No, that's different. So, I think the cheesy lock has more specific information on garbage collection. Um, this is just, I think, kind of a subset, or uh, maybe use this. I think Andreas knows a bit more on this topic than I do. Any other questions? Yeah. Okay, so the idea was I started looking into how to make an easier usable profile that also integrates into your IDE, because I thought this is really important also for people that want to profile surely. I looked into what possibilities I had, and the problem was that I didn't want to reinvent the wheel, and I came over Firefox profile and saw, hey, they have an open data format. I talked with them in their Matrix chat and asked them, hey, I have this idea, I have this small prototype in like 2 days that converts from JFR data into this data that the profile uses. Would you be fine with me like adding some more features, like here the function table and so on, more features that make it usable also for Java? And they were like, yay. And it was like, cool, then I work on it. So it's essentially based on necessity, because reinventing this whole thing and rewriting it is really hard, because uh, you also need people to review your code, and the Firefox profile will kind to review my code, to work with me on it, to improve the code here. And also, I think many people use Firefox profile already when you're doing web development, and it also allows us later to integrate other data sources. For example, one could combine this with the data source from your browser with Power Profile, and then you see, oh, I click this button there, and then on the server side, add this stack trace. So this might be quite cool. Any other question? What? No, no, I'm not doing a PhD. Hell, not. I tried to do a PhD, but I didn't do it till the end. I think there are people that got their PhD and are quite happy, but I'm quite happy that I'm now at this team. So no, it's a thing that I worked in the summer at SAP on it, because yeah, as I said in the beginning, I'm working there since January as a full-time developer. Any other questions? Or do you want to say other tools? Okay, cool. Um, then I try to get out of this exit presentation. Oh, this worked. So whatever here. I think that's even less legible. I think I could just change the monitor resolution to make it work. Uh, uh, I hope this doesn't blow up. So sorry for the reduced resolution. I hope it's now easier to read. Cool. Because yeah, web technology kind of works with increasing the font size. This definitely doesn't work. This is JDK Mission Control. Um, it is based on Eclipse, and it has therefore also the capability of Eclipse, like with these tool windows and everything. So here we can load the file. We can just open the juk file, code charts juk. We can open the same file. Cool. So you see here, it does this automatic analysis. It tells us here that hey, the JVM paused like 76% of the time, because the GC pressure was like at a value of 97 out of 100, and maybe the maximum use memory was like 99.5%, and but it's an example. I thought it's interesting. So you can get into method profiling. You can get also into like memory profiling. For example, so you see here the garbage collection and also some other memory. So for example, you see the used heap as this violet curve here, and you see that the used heap essentially every time, I think it's every time I called this read all files method, because it got all events, it started to go up the heap, and then the garbage collection came in and put it on, but essentially you also see that the garbage collection went every time here because, yeah, it was my JVM was kind of out of memory. You see here also the objects that were allocated and how many total allocations there were. You see, for example, here that the recorded event, this was like the event class that was read from the file, amounted to 2.8 gigabytes of data. And then you had also some indistinct object files. You can see here below where it was allocated, so you see, okay, it's also in this like event parsing stuff where it allocated. What's also cool with this, you can use it to connect to a JVM. We can just connect to the to this mission control it's on. We can have different possibilities, like having a console. That's quite interesting. Where you can see what the JVM does. So we see currently what the JVM that runs this mission control does. We see its CPU usage. We see some small data points. We see that probably something should change when you're clicking here frantically at something. No, it doesn't, but you get a picture. So what we also can get is we can connect to this JVM and get a heap dump, which is sometimes really, really great because we can again in-depth analysis of the current allocations of the current heap. And you see here what, for example, JK Mission Control usually does. It allocates what the
Okay,
it
yes
allocates
is the
every
answer of
lost
the
and
expert.
has that.
Thanks.
As every, I think it does.
Yes, of
Oh,
course, you
no,
can
it allocates
configure
to
everything. So
mostly.
yeah,
Don't know why. Maybe
you
all the
can
screens
configure
show
all the
here.
tools here to do
And you can
to
get
do
more
everything you
information on
want,
this,
especially when
also
you're coming from
specific
online.
tooling
So
on
yes, this
analyzing
is
heaps, but I don't show them
JMC.
here. Yeah, and it has lots of more features and visualizations. Just take your time to explore it. I put I think 2 talks and 1 slides in my recommended resources. They show you more They show you more information. Any more questions regarding this? There's the cube. Yes. No, no, no. It's the actuator for Spring Boot is a project of an individual who did it for I think for his company work for Spring Boot, and this gives you the JFR file. So you can have this like JFR start and this JFR dump, and then you can download the file, put it into JMC, and are fine. And it also allows you to create frame graphs. Yeah. Any more questions? Okay. Then I think I can just then try to show you how Async Profiler kind of works. It's not that it's not that hard. I created a demo app for this. I created the demo py so I don't have to type in the whole commands. You can look at it. It's just a simple version of for using Async Profiler with all these options. I would really recommend when you use Async Profiler or JFR regularly, just make yourself some aliases to make your life a bit easier. For example, here we try to profile the new version of our application. I think it's so now it's hopefully readable. It's here this line. We start the Java application and ask our event filter up to it is like the modified version, and then just tell it to produce a JFR file. And these are the actual arguments that I used for the sample application. So it's just a really simple regular expression and a large file. So it starts. So you see here that the options that I pass to to Java, I like this unlock diagnostic, VM options, and debug non-safe points. And after I told you about what safe points are, you probably now understand also why I want to add this, because it tells you, please, between safe points also give me some more precise information, and not only on safe points. So if you remove these flags, you only get real information on the safe points, and between them it's a bit more fishy. And then I passed it the Asian path and told it the interval. You can you can decrease the interval at JFR to like 1 milliseconds, and Async profile supports like far lower. I run it with like 10 microseconds and it kind of works, but the problem is when you're getting too low, you're essentially interrupting the thread when it's in the signal handy, and you're interrupting it to get the stack trace, and you're interrupting this to get the stack trace, and so you're essentially just profiling the stack trace getting kind of, so it's a bit weird, but it's good to test the underlying code. So we got here the JFR file, and then Async profiler contains an application. Then Async profiler contains an application that I also wrapped here that's called a converter jar, and that you can use to convert the JFR file to the flame graph. So it went quite fast, and then we can open it. I hope it works. It works. So app2.html. I think I should. Oh. Does end? Oh. Yeah. Hope this doesn't. Oh. Okay, it does open my whole browser. That's not what I wanted to. Sorry for that. But yeah, you see here the flame graph as you've seen before. It's a pretty simple flame graph generator. It generates the flame graph in C. It has some built-in strings to create it, and you see the whole flame graph. You can even be a bit more interactive. You see here, I think I can increase the size. You can see here the specific information, like, okay, this is the function get events. It had 1000 samples, and this method has 229 samples, and that's the way with which I got to the numbers here, and you can click it and zoom in and work your way up. Yeah, I think. Does anyone have questions for this Async profiler? Okay, and now to the end of the presentation. And now to a bit funny in the end, because I thought like this is really technical and it's really dry and so on. So I have a video. So for the context, there's the person that like popularized the flame graphs. He's called Brent Neck, and his Wikipedia biography kind of ends with this sentence, and he's also famous for being the star in the video "Man Shouts in Data Center." And I was like, during my research for this talk, what's this video about? And I found it on YouTube. It has like 2 million views, and yeah, it's essentially a profiler writer that has fun, or not a profiler, but a data analysis person that analyzes performance, shouting in the data center, having fun. And I thought maybe I could end this talk with this. I hope.
Hi, I'm Brendan. We're here in the Fishworks lab. Sorry for screaming, it's very loud in here with the air conditioners and servers all around me. We just made an interesting discovery and we thought we'd show you straight away. So over here I'm measuring disk I/O operations broken down by latency. I've also drilled down to disk I/O operations taking at least 520 milliseconds broken down by disk. This is using dtrace so I can do performance analysis of disks. I'm applying a write workload to 2 JBODs, which are over here. The lights are blinking on these JBODs because they're doing work. What I'm going to do is not recommended. This is not supported. Do not try this at home. Ah! Ah! This is not special effects, this is real. What we're looking at here is the effect of disk vibration. Vibration is a serious issue, and we can see the effect here that it's caused. So here, the latency for the disks that are under the workload has gone up. Here I can see which disks have now had I/O operations longer than 500 milliseconds, and I can find out that they belong to the JBODs I was just shouting at. So, amazing stuff. This has been made possible by analytics from Fishworks, which lets us look at things we've never seen before. Disk latency.
Yeah, so I don't recommend you shouting at your hard drives. I think it doesn't work with SSDs. I haven't tried it, but yeah, you see that profile writers are quite funny people. He kind of popularized the flame graphs, and he did lots of things in this area. So he's really cool around. So I would really recommend also watching other talks of him. And yeah, and now, sorry. Eh? That's the problem with hitting enter. So now, thanks for your patience of coming with me through this voyage on profiling, and have a nice evening and a nice pizza.